Hello and welcome. This is Howard Moore, Chief Meteorologist at StormQuant, and we're joined today by members from the Florida Department of Emergency Management and members of the National Weather Service and NOAA to talk about StormQuant and FDEM's effort to put X-band weather radars at a number of key locations in the state of Florida. So thanks for joining us.
The brief background on me, I am an Air Force veteran, over 20 years of operational weather experience, supporting fixed wing, rotary wing, command and control, and a number of other types of missions. I've been with StormQuant for approximately 2 years now, and I'm very excited to share with what we're bringing out to you. So let's begin. Here's an overview. We'll start with the hardware overview and capabilities. We'll discuss the deployment locations throughout the state of Florida and the updates with the counties and where we're at. We'll show you what that radar coverage that results in, or is expected to result in. And then our software overview and a demonstration of the software. And then finally, we'll wrap up with some questions and comments. And so let's get started here. So this slide shows you some of the specifications, gives you a little idea of what we have here. We have an X-band radar, 9.3 to 9.5 gigahertz, 6 channels, a pulse width of 0.5 to 60 microseconds, dual polarimetric. It's 120 VAC input power and 2.4 kilowatt pulsed output power. It's about the size of a small refrigerator and weighs about 250 pounds. For sensitivity and reflectivity, we can detect 18 dBz out to 93 miles and 0 dBz at about 28 miles. And that 0 dBz at 28 miles specification was developed in collaboration with the 45th Weather Squadron out at Cape Canaveral Space Force Station. We worked with them to develop capabilities where they could use the radars in support of their launch operations. And that was on our first iterations of the radars, and the ones that are being built now are being built to that spec. Data formats, we have multiple data formats. We can get it any format that's needed by the user. Our 3 dB beam width is at 1.6 degrees, and that is with super resolution. And our rotation speed, we can go anywhere from 0 to 30 RPM. The design of our antenna, we have a feed horn going up to a parabolic reflector plate, going down to a splash plate that rotates and tilts. We rotate that at approximately 12 RPM for standard weather surveillance, but it can be sped up or slowed down as need be. In addition to being sped up or slowed down, it can also be changed from a surveillance standard scan mode to a range height indicator or simply a sector scan very rapidly because of the light weight of the splash plate. Okay, we'll move on to the next slide. For our FDEM deployment locations, you see 3 different counties that we're looking at here. In the northern portion, we have Marion County and Flagler County, and we're looking at placing them at the emergency operations centers of those counties. And in the south, we have Collier County. We're looking at 2 primary locations there, one on Marco Island on top of one of the condominiums, and another is at the Everglades Air Park in Everglades City, Florida. And we'll go into a little more detail on those. So for Marion County, this is an overhead view of the location along with a side view of their tower there. They have a self-supporting 150-foot tower, and the structural analysis on that tower is already complete, and we have verified that this can support our radar. They are currently moving some of the antennae that are on the top down, or removing some of the old antennae that are not needed anymore. But we expect to be installed no later than 30 June of this year. Moving on to Flagler County. In Flagler County, similar to Marion County, we're at the Emergency Operations Center on this tower. This happens to be a 100-foot monopole tower. Again, the structural analysis is complete on this, and we are thumbs up to install our radar at this location. And then finally, for Collier County. I mentioned there are 2 locations. You see the bottom center of the image shows an overhead picture. That's the Cozumel condominium. They currently support some naval equipment on top of their roof and are willing to support our equipment there. We're in the process of working with the Navy to ensure that there's no conflict of signals and power between our system and theirs. If for some reason we find we cannot put at this location, the alternate location we're looking at is on the bottom right there at the Everglades Air Park. We have looked at surveyed both of those sites, and we are would be able to put there at the Everglades Air Park if the condominium is a no-go. At all of the locations, we're coordinating with the local POCs from the emergency services. We're evaluating power, backup power capabilities, communication capabilities, as well as the structure. We also have teamed up with LNS Enterprises. Have experience in climbing specifically the towers that we showed you in Flagler and Marion counties, and have experience all over the state in supporting, installing, and maintaining hardware on towers. So a wealth of experience that we've teamed up with LNS Enterprises. What does that result in? That results in this radar coverage. You see the two locations in the north that are overlapping each other, and then the one in the south. This particular image and the one in the Collier County, we selected the condominium location just to simplify the image. Each of these has a radius of 93 miles for the 18 dBz detection range. Okay. So that's a bit of the hardware. Let's move on to the software here. So for our software, there's a lot of information on the screen. And I won't go in detail on each one of these, but I want to highlight three of the key elements that I believe set us apart from our competition and help improve what you have or improve the type of visibility or visualization that you have today. The first is for meshing. As you see that under features, it says data from StormQuant, NextRad, and TDWR sources. We can already ingest certainly our own data, but if we can ingest NextRad data, we can ingest TDWR data, and we can mesh those into a single grid. And when I say mesh, it's not simply taking the radial imagery and then overlapping them on the same window on the computer. What we're actually doing is we're taking the radial data, converting that into a cubed grid over the selected region, the user selected region. And then if you have multiple radars, then combining that data in that grid and then overlaying it over the geographic location you selected. And if there's data for multiple radars within a single grid cube, then we're taking the maximum value within that cube from any of the radars, and that's the one that's being displayed. So what does that do? Well, one, it helps the user. You don't have to open, if there's three different radars over an area that you want to evaluate, you don't have to have 3, 4, 5 windows open at the same time. You can have a single window and get all the data in from those radars. And of course, we know that radars hit at different angles to different meteorological phenomena. If you have all of these radars hitting from all different angles over a single geographic region, you've combined that into one cube. What you do then is you don't have to worry about whether am I looking at this from this radar? What parts am I missing? Am I looking at this from this radar? What angle am I hitting this at? You've got all angles represented within that data cube that you're looking at. In addition, with the X-band radar, there is a natural attenuation of signal. So with multiple radars looking at it from the same weather phenomenon from different angles helps mitigate the amount of attenuation that occurs. So that's part of the meshing. And I'm going to display this when we go into the demonstration portion of it, this briefing. Another part I want to draw attention to is for our speed of our 3D visualization. First of all, the fact that we can have 3D visualization, which you can see in the image on the left, there's a 2-dimensional view, and then there's 3-dimensional views from both our radar and from a NextRad radar. And it's actually showing a vertical cross section there. So that 3D voxel slicing or vertical cross sections, we can do both in the vertical and the horizontal very rapidly at any location that you want to see on the map. And I'm going to show you that in the demonstration. That's the second thing. And then the third thing I want to draw attention to are our user-defined alerts. So what we have right now is for our reflectivity and our velocity values, a user can click a location on the map, can set up a radius from that location, and define a threshold for the weather phenomenon. And then the system will alert when that threshold has been exceeded. And we can do this in both the 2-dimension and 3-dimensional space. And we'll show you that as well. At the bottom of the screen, you see our base products, which will all be available when we actually deploy at the end of June. And then the derived products, which will actually be available at a later date after our installation. So I'm going to pause there. I'm going to minimize the slides, and we're going to bring up our weather dashboard. So what you're seeing now is the StormQuant weather dashboard. There are three viewports or windows that we have open. The left-hand one is showing a three-dimensional voxel view of reflectivity data looking from the south towards the north over the Cape Canaveral along the Florida East Coast. You can see Melbourne to the south, Palm Bay. On the right-hand side, we actually have, and I'm sorry, let me go back to this left-hand image. The left-hand image that we're three-dimensional view is actually a meshed view of radars from StormQuant radars from North Cape Canaveral Space Force Station, South Cape Canaveral Space Force Station, and the Melbourne NextRad radar. So we have three different radars meshed into creating this data imagery that you see on this left-hand side. On the top right, you see a live view of three NextRad radars out of northern New York, and that's showing a little bit of rainfall over here in southern Canada on the top left of the image at this time. And on the bottom right, we have a radial image of the Melbourne NextRad data out of Florida, and that's historical. So the first thing I want to do is draw attention to the highlights of those elements that I had described on the screen before. We talked about the meshing, multiple radars. So see here right now, I'm going to turn off, just toggle off the Melbourne radar. Now, at the time that we had our radars, the StormQuant radars, these were only going out approximately 45 miles from the location. So you see we have data from our northern radar and our southern radar over the Cape. I've turned off the Melbourne NextRad radar. I can toggle off our north radar or our South Cape Canaveral radar. You can see how it fills in spaces there, and then bring back the Melbourne radar. And that's all three radars viewing it at the same time. So again, helps for the mitigation of X-band signal attenuation. It also then helps from different elements of three-dimensional angles that you have from multiple radars seeing the phenomenon at the same time. The second thing I want to draw your attention to are our cross sections. So on the top, I'm going to go up to filters, and I'm going to click on horizontal volume slice. And when I do that, I toggle it on, notice that the tops of the storms have been sliced off there. I'm going to click on the gear icon, and it's going to show me at the altitude that it's sliced. Right now it's at 24,000, a little over 24,000 feet. Now I could take my cursor, hold the button, and simply drag to change the altitude I want to look at, or I could double click and type in a specific value. Now on the image, if I want a closer look, I can just zoom in and take a closer look at any portion that I want to. Okay. Now that's for obviously a horizontal volume slice. So let's look at vertical volume slice. So go back up to filters, toggle vertical on, and you notice that it puts a tool on my screen here, a little white square. I'm going to click on that, and it gives me a green square and a green circle. That green square allows me to move this tool anywhere on the map. What the green circle does is it allows me to rotate my slicing tool at any angle I choose. So very rapidly at anywhere in this image, we can quickly create vertical and horizontal volume slices at any location, and then simply sweep in with our view to take a look at what that looks like up close. I'll go back to my horizontal, and let's raise it up and you see inside the storms there. Now that gives you as the user quick ways to interrogate within the storm. Now in addition to the vertical and horizontal volume slicing, on the right-hand side of the image here, we have our filter bar. I can place my cursor on the filter bar and simply filter out the level of intensity and reflectivity that we're viewing. That combined with our volume slicing is a very useful tool for evaluating what's going on inside the storms. So we'll turn those off. And the last thing I want to talk about here, as far as our key features that set us apart, are our alerts, our user-defined alerts. So right now I'm going to click on the screen. Prior to do that, I'm going to go up to the top here and I'm going to insert a three-dimensional object, and that's going to be a launch trajectory. Okay. Now I'm doing a launch trajectory. This could be a flight path. It could be instead of a launch trajectory, we could insert a flight path, or it could be something on the surface, such as critical infrastructure, a pipeline, or it could be point locations, such as nuclear power plants. Any point location on the surface or a pathway within three-dimensional space can be added in here. So now we have a nominal flight trajectory out of the Space Coast. And now I'm going to click on the map and I'm going to add our detector. Okay. We'll go to the top. We can choose cylinder area detector, which is for a two-dimensional image, or trajectory detector, which is for a three-dimensional image. We'll give this a name. We'll just call this launch, and we could give it a description if we choose. And now I'm going to import. I'm importing the same trajectory that we see on the map into our detector tool. And notice here it's loaded at 125 points. So that means there's 125 points along that trajectory that we're going to evaluate against. And now I'll go to my detection area, my radius. I can put in any distance I want. Let's put in 6. And notice it's in kilometers right there. And then I'll choose a minimum threshold. Let's put 52 dBz and click OK. Now, if you notice on the map, and I'll zoom in, give you a better view, what we've got here are alerts, visual alerts that are triangles. And as I run my cursor over them, it gives me information about it. In this particular one, it says a value of 53. So that's 53 dBz. It shows me an altitude of 17,104 feet and a GPS latitude and longitude in decimal degrees of that threshold violation. And each of these is an individual threshold violation. And again, remember, we're looking at 3 different radars here. So it could be from any one or multiple of these radars that we're getting that from. Okay. Now you say, okay, there's something happening here that exceeded my threshold, but now these are in my way for me seeing what I want to see. I want to filter out and view it in more detail. Well, what we can do is we can go up to our overlays, go to detectors overlay, and just simply toggle them off. Now we can go do our volume slicing in the vertical and horizontal, do our filtering to see what's happening here. And then if we want to see those again, we can turn them back on, and they're back on the screen. Now on the top right, you see a little bell icon with a red circle on it. If I click on that, it says alert notification, and then I can go down to my details. What that brings up is the tabular data of the alerts that we had. And so these same alerts that you see on the screen in the image are now in this table, and it gives us the threshold value, the latitude and longitude, and the altitude at which that value was detected. Now, we're just seeing a visual indication on the screen here. We could tie this in and have, excuse me, have audible alerts. Excuse me. We could tie this in with audible alerts as well. Or we can tie this in with APIs and other programs to where when this alert happens, it actually is via APIs to other programs. It could be sending out emails. It could be sending out text messages. In this particular case, this is on a launch range. So this could be sending signals to indicate lights or klaxons at specific facilities on the Cape to alert people that there's some weather that they need to be aware of, or there's processes they need to stop, or safing processes they need to start. And this has radar data. Again, I told you it was reflectivity or velocity based. But as we develop our additional tools, such as for precipitation estimations, we could have this for flash flooding potential. As we also expand our sensors that we're incorporating into the software, such as lightning detection, the alerts could include lightning detection nearby. So what that could result in is the user could develop a alert for a specific type of mission that includes multiple phenomena at the thresholds that they've determined at multiple locations, or either at multiple point locations on the surface, or again through three-dimensional space, and create their own tools for their alerts to have them to be notified, or to have anybody they want to be notified via additional app. connections. So right now I'm going to go up here. I'm going to hide our detectors. I'm going to expand. Now the three I went over, we went over meshing, the three-dimensional voxel view and slicing for our cross sections, and now our alerts. I'm going to show you a couple of additional tools that are what I would consider standard tools that you'd want for any type of user software for weather, but I still think they're important to note that we have them and they're available for your use. And the first one is here. I'm going to click on the map. Now we're looking, of course, at two-dimensional reflectivity from the top down. And I'm going to right-click on the map. I'm going to add range ring set. Now what that's done is put a set of range rings here right where I had it clicked on the map. If I go to the left-hand side under World Objects, I can go down to my range ring set, and I can lock it in place if I choose to. I can give it a name. I can change the specific location by double-clicking and putting in the lat long that I want, or again, I can hold down and I can simply slide my cursor in here, and it will adjust to where I want it on the map. Now for each of the range rings, I can go in, I can set a specific color for each range ring if I want to highlight or just give a better visual indication for somebody looking at the map. And again, when I clicked on that was kilometers that it's set in here. Let's say you don't want kilometers, we can go up to the top on the left-hand side under our global menu, and we can change our display units. And so for our distance, it's in kilometers right now. I can go up to feet, meters, nautical miles, change it to nautical miles. As soon as I do that, go back down, my range rings have changed to nautical miles, and it reflects on the map as well. And of course, we can go down to hide those range rings, or we can simply delete the range rings altogether. We can do similar types of functions with GPS markers. We can set GPS markers at a specific location and do the same type of customization on the left-hand World Objects menu. Now we can also use what we call the tool tracker pins. We have a tracker pin. We want to know, okay, this phenomenon, how close is that to my operation at this location here? I'll click on that tracker pin and have it highlighted. Go to my new place on the map. I will right-click, add, and notice my linked tracker pin is available because I had selected the first tracker pin. Now I'm linking a second one, and that's allowing us to show a distance between those two pins. So each of these types of tools is customizable to the user and available on any of the maps. And then finally, I'm going to show you here on the top right-hand side, we have multiple types of products we can look at. Let me maximize this a little bit for you. And on the top, we have differential reflectivity that we can bring up. Of course, we've already looked at standard reflectivity. We have velocity. And if I go down here, we have an elevation tool, and we can go at different elevation angles. And then we also have spectrum width to choose from. And of course, future products are being developed right now and will be included as they're complete. So I'm going to pause now for this part of the demonstration, and we're going to go back to the slides. So we've showed you the hardware where we're planning to deploy it. We showed you the software that's coming. And what's coming in this contract with between StormQuant and the Florida Department of Emergency Management are 10 licenses for use of the software, the 3 radars at the locations noted on the map. We're showing the coverage, in addition to 24/7 hardware and software support. Now, the locations of these radars were placed there because we're trying to fill in some of the key vertical gaps in the current infrastructure of the NexRad and TDWR location. If this is as successful as we believe it will be, and the FDEM believes it will be, we think that there's future potential for expansion in Florida.
The image you see here shows the state of Florida covered by 18 StormQuant radars, ensuring that the entire state of Florida has coverage. At $4 million a year, that's a fraction of the cost what it is to run the current infrastructure that's in place. You could significantly improve the low-level detection by adding these radars. In addition, because of the remote capability to control them, we could go have a number of radars in standard weather surveillance mode while having other radars transition to RHI or sector scanning for detailed analysis of the weather. The radars are hot swappable, and we can have standby radars in place and ready to go for swap out times less than 4 hours at a location, significantly reducing the amount of time it takes to get radars back up and in place. Note that the current infrastructure, for example, in Louisiana, for the loss of the Lake Charles radar, in Puerto Rico, the loss of the radar there was 5 to 9 months of dead time with those radars out when they were damaged. This image indicates the outage of one node or one radar in the network of radars. And while you will lose a level of vertical detection with that radar being out, notice the horizontal coverage is still retained. And by having these multiple overlapping radars, if any one particular node goes down, you have a graceful degradation of the network, and you still maintain a significant coverage of the areas. In addition to having the graceful degradation, you also mitigate attenuation by having multiple radars overlapping each other and viewing the weather from different angles. And on our final slide, you see two images here. On the left-hand side, you see our radar on top of our 35-foot Scorpion tower extended. On the right-hand side, you see our radar in the back of a standard pickup truck and the Scorpion tower folded up on a flatbed trailer. The size and weight of our radar make it easily transportable and rapidly deployable. And once we arrive on site, we can have it up and running in less than 20 minutes of time. Excellent for situations where you have extreme events and you need rapid radar coverage due to an unexpected outage.
And this slide here shows on the top left, our website. Below that, our YouTube channel. On our YouTube channels, we have some different videos published. Some are simply visual to show some of the visual aspects of our software. Others are actual tutorials that I've created to help with different aspects of doing a specific function within the software. And as we make modifications and improvements and additions to the software, we will create additional tutorials and post them on this YouTube site. On the bottom left is our address for headquarters in Titusville, Florida. On the right-hand side, we have information for our CEO, Mike Warren, our president, Tristan Rizzi, and myself, and our email addresses. And we encourage you to contact us if you have any questions or concerns about any of this, or if you have later on, you start thinking about what we've talked about today and additional questions come up, please let us know. Okay. And now I'd like to address, we have a few questions that were asked, and one of them was talking about, can we get this data, or our StormQuant data, into a GR2 and AWIPS? Well, first of all, we can already format our data to be visualized in GR2, so that's already complete. Regarding AWIPS, we need to know, as long as there's an API, way for us to talk to AWIPS, and we know the format that AWIPS needs to visualize it in, we can get our data and format it in that way. So getting the data into GR2, what already done into AWIPS, it is a doable function for us. We would just need some additional information for that. And then it'd be just a matter of permissions, right? Those folks in charge at the NOAA National Weather Service sites or at other DoD sites where AWIPS exists, if they wanted our data in there, we would just need to be able to talk to the individuals who are in charge of the authorizations, the permissions, and the formatting, and we can make that happen. We had another question about attenuation and rain fade. Naturally, with a X-band radar, you're going to have some level of attenuation. That's just part of the physics. But there are things you can do to help with that, either to mitigate that in some aspects and eliminate it in others. Things we're looking at right now to implement are linear fit attenuation mitigation. as well as self-consistent procedures at specific radial distances. And so those will be added to our software as we develop it. Mhm. Thank you for joining us today. And again, please reach out to us for any questions and look forward to meeting you all when we can. Thank you.